Well, now is the time to apply the principles and theories that we have gone through regarding simple harmonic motion. In the case of simple pendulum, you see, it is the simplest oscillator you are coming across the very first time. What is simple pendulum? If I consider that you know it, you must be knowing bob, the string, uh, point of suspension, or you might say the rigid base. Could I say a bob string and rigid base together make simple pendulum? No, not the least. Suppose I hold in my palm a bob or string and a nail or rigid base, whatever you call it, and I close this wrist. Is it the simple pendulum in my hand? No. So you must be clear that when you are using the term pendulum, it is ready to oscillate. Unless there is the freedom to oscillate, you can never assign this term oscillator. Oscillator means it is ready to oscillate. Soon as you give the jerk, you give the push, it will immediately start swinging. Then it is always ready to oscillate. See, this is a bob, heavy mass, a string, inextensible and very light. We don't consider even the mass of this string. This system itself and free to oscillate is called simple pendulum. You see, when we consider the length, when I close my two wrists, the distance between these two would be from the center to center. Similarly, if you consider the distance of the bob from point of suspension, obviously you'll have to go up to the CG of this bob. So, effective length of this pendulum will always be the length of a string plus the radius of this bob. Now, suppose this pendulum that is freely suspended is displaced a little from its mean position. Then what happens? It's a weight. Suppose you have given the displacement theta. Remember, the whole chapter of simple harmonic motion has one assumption already imposed that displacements will always be very, very small. The angular displacement that we are considering here can never be greater than 10 degree. If it is up to 5, it's very nice for our results. See, the angular displacement is theta. You have put the pendulum up to this position. Now, we'll resolve this mg, that is weight, in two components, mg cos and mg sin theta. Actually, out of these two components, you might have noticed this is responsible for bringing it back to the mean position. Obviously, mg sin theta is only the restoring force. Restoring force here is minus mg sin theta. Force is m into acceleration. This is minus mg. And considering the angle very small, sin theta could be approximated to theta itself. M gets cancelled and theta, angle, that is arc upon radius. This arc could be the displacement here and length of the pendulum. So, you could write here minus g upon x upon L. This is in place of theta. You see, you know already the characteristic of SHM, that is alpha minus omega square x. In place of omega square, you are finding here g upon L. Put here omega square equal to g upon L, you get omega root g by L. And if you take this as 2 pi by t, you get this result finally, that is giving you the value 2 pi root L upon g. This is the formula for simple pendulum, time period for simple pendulum. One condition is already imposed here, that angular displacement is very small. Not only that, this pendulum too is very, very small in length. You see, if you consider the length of pendulum very, very large, it's going to be limited time period. Then in that case, it is going to be 84.6 minute only. So, two conditions are there. Pendulum should be very small and the angular displacement should also be very, very small. Other things have been mentioned here. You see, if you want this in terms of, here we have been considering linear displacement, linear restoring force. In place of that, if we consider the angular form, then we are going to consider this angular acceleration. Angular acceleration could be obtained from restoring torque. Restoring torque will be equal to I into alpha. Restoring torque could be written as force into perpendicular distance. As I told you, force would be mg sine theta and perpendicular distance will be L. Then in that case, time period, this torque would be written as mg sine theta into L, and this will be I alpha. I will be ml square alpha minus mg L. Sine theta is going to be x upon L. But you want to retain theta, then don't replace it. You want the whole thing in form of angle. So sine theta will be retained as such. As theta, you could take m and L common both side. Alpha you finally get here minus g upon L theta. This is again angular acceleration and angular displacement.